This equation looks like a nightmare. An x in the base and an x in the exponent. But note, since 3 to the x is always positive, we need x to the ninth power to be greater than 0, which means we restrict to x greater than 0. This is a banger of a problem, and the solution is one of the most elegant tricks in algebra. Now, your first instinct is probably to use logarithms to deal with the exponents. Logs do lead to the exact equation, but it's transcendental and needs Lambert W to solve. Let's see why elementary algebra hits a dead end. We start with our equation. Let's take the natural logarithm of both sides to bring those exponents down. This is valid because we're restricting to x greater than 0. This gives us the natural log of 3 to the x equals the natural log of x to the ninth. Using the power rule of logarithms, these exponents can now become coefficients. We get x times the natural log of 3 equals 9 times the natural log of x. We can rearrange this as natural log of x divided by x equals natural log of 3 divided by 9. And here's where elementary algebra hits a wall. To isolate x, we'd still have x on one side and the natural log of x on the other. This transcendental equation can be solved exactly with Lambert W, but not by simple algebraic manipulation. We need a more clever approach. Let's rewind. Instead of logarithms, we can manipulate the exponents to find a beautiful symmetry. Starting again with the original equation, our goal is to get this into a symmetrical form, like a to the a equals b to the b. Let's raise both sides to the power of 1 over 9x. This is valid since both sides are positive and 9x is not 0. This looks more complex, but watch what happens when we simplify the exponents. On the left, the x's cancel. X divided by 9x equals 1/9. On the right, the 9's cancel. 9 divided by 9, x equals 1 over x. Now we can simplify these fractions. On the left, x divided by 9x equals 1/9. On the right, 9 divided by 9x equals 1 over x. Simplifying the fractions. Look at that. This beautiful symmetric form is the key to the entire problem. But here's a crucial point. Just because two expressions of the form t to the 1 over t are equal doesn't mean the t values are equal. The function x to the 1 over x is not 1 to 1. For example, 2 to the 1/2 equals 4 to the 1/4, since both equal the square root of 2. But clearly 2 does not equal 4. Before we solve, let's understand the function y equals x to the 1 over x. How many solutions can we expect? Let's create a coordinate system to visualize the behavior of our function. We'll use an x-axis from 0 to 35 and a y-axis from 0 to 1.5 to capture the full picture. First, let's plot the function x to the power of 1 over x. This function has a unique bell-shaped curve with some fascinating properties. By calculus, this function has a maximum at x equals e, where the value is approximately 1.445. This maximum point is crucial for understanding our solution. Now let's add the horizontal line at y equals 3 to the 1/9, which is approximately 1.130. This constant value is what we need our function to equal. Since 3 to the 1/9 is less than the maximum, the horizontal line intersects the curve exactly twice, once before e and once after. Here are the two intersection points that we'll find algebraically. The graph shows one solution is much larger than the other. Let's find that integer solution by exploiting the symmetrical form we just derived. We are looking for a value of x that makes this true. The trick is to ask, can we rewrite the constant on the right side to be in the same form as the left, something to the power of 1 over something? We can multiply the numerator and denominator of the exponent by 3 without changing its value. This gives us 3 to the power of 3 over 27. Now, using the reverse power rule, we can rewrite this as 3 cubed, all raised to the power of 1 over 27, and 3 cubed is just 27. And there it is. The equation is now perfectly symmetrical. By inspection, x equals 27 is clearly one solution, since both sides equal 27 to the 1/27th. We find our first solution, x equals 27. This matches exactly what we saw on the graph. Let's quickly verify this in the original equation to be absolutely sure. We need to check if 3 to the power of 27 is equal to 27 to the power of 9. We know that 27 is just 3 cubed. So we can substitute that into the right side. Now, we multiply the exponents 3 times 9. And we see that it is a perfect match. Our solution is correct. Now let's find that second solution using the Lambert W function. We start from our rearranged log equation. From our earlier logarithmic approach, we had natural log of x over x equals natural log of 3 over 9. Let t equal natural log of x, so x equals e to the t. Then our equation becomes t times e to the negative t equals natural log of 3 over 9. Multiply by -1 to get this in Lambert W form. The Lambert W function gives us t equals -w of negative natural log of 3 over 9. Since negative natural log of 3 over 9 is between -1 over e and 0, there are two real branches. The w sub 0 branch gives x approximately 1.15082482213. The w-1 branch gives us our integer solution, x equals 27. In summary, the equation 3 to the x equals x to the 9th has exactly two positive real solutions. X approximately 1.15082482213 and x equals 27. The integer solution emerged from our elegant symmetry transformation, while the exact forms involve Lambert W functions. Now that we've found both solutions algebraically, let's visualize them on our graph to confirm our work. Here's our function x to the power of 1 over x and the horizontal line at 3 to the 1/9. Perfect. Here are our two solutions. The smaller one at approximately 1.151, found using Lambert W, and our elegant integer solution at exactly 27. The key was not complexity, but finding the right perspective. By transforming to a symmetric form, we uncovered the beautiful integer solution hidden in plain sight. Thanks for watching. If you enjoyed this deep dive into algebraic problem solving, please like and subscribe for more math content. See you next time.